Right. So we are dealing with the geometric and timing aspects of robot motion, right? Particularly um, robot manipulators, right? So you know that it's a three-dimensional geometric problem, right? So you have number of links and adjacent links are connected with actuators. And then when you actuate a certain joint, the lower end link works as the reference and the upper end link works as the relative link, right? Reference and relative. And the relative link moves, right? It can be a rotation, it can be a linear motion depending on the nature of the joint. So we need to have mathematical framework to describe or calculate the motions, right? Particularly the end point, finally, right, from the base to the end point of the manipulator, right? All of these joints, where they are in space, okay, what direction are they looking at? And more than that, at the end of the manipulator, there is a tool, right? You're using a manipulator for a certain application, maybe painting, cutting, seaming, handling objects, etc. So you're gonna attach an end effector to the endpoint. So you need to know what's the position of the end effector and where it is looking at, the orientation, the direction. All right. So in previous lectures, you learn about the orientation representation. There are various ways to do that. Okay. And today we're going to look at this geometric problem of the manipulators, right? How do we calculate the endpoint position and orientation, and also for that matter the position and orientation of any other link in the manipulator, right, from base to the end effector. And second bullet over here, right, we assume open chains, which means robot has a base which is connected to the ground, or maybe on top of a table, or it can be on top of the ceiling, attached to the ceiling. There are some manipulators attached to the ceiling, okay? And then they are hanging down and operating objects on the ground and on top of tables and around, but very rare. So most parts of the lecture and also for industrial applications, base is the ground or on top of a table, okay? So we need to have some idea about the workspace, right? That is the three-dimensional space around the robot. You can assume robot's base, manipulator's base is at the center, right? And also calibration, right? There's some sort of joint angle calibrations, right? Where is the zero, for example, right? If you think of a robot joint, what is zero, right? You can think of your upper limb, right? From the shoulder to elbow to the wrist and all that. When you fully extend the arm, you can say this is my zero position, all the joints zero, right? What about the shoulder joint? You can say you can you can raise your upper limb up vertically upwards, right? And you can say this is my zero home position. I start measuring the angle, shoulder angle from the vertical position. Or you can say, no, I want to hang it down, right? From the vertically downward position. So this is my minimum energy position, right? My joint zero angle is that. Fine, that's all right. So there's some sort of convention where is zero and what is the minimum angle that every joint can move, right? And also you need to have some idea about the task execution, right? Uh, Manipulators are moved by motors attached at the joints, all right? You can have 5 joint manipulator. We call it 5 link manipulator or 5 degree of freedom manipulator. number of joints, number of links, right? Number of degrees of freedom are generally same. Not always, generally same. One exception where this is not the same is when you have multi degree of freedom joints. For example, there are so many multi degree of freedom joints in human body because human body is a very, very complicated anatomy, right? If you look at your shoulder joint, you have 3 degrees of freedom there. It's like 3 motors in orthogonal directions, right? 3 motors working on top of each other, but they are intersecting at a single point, that is the shoulder. Okay. So if you want to do it in like artificially, right, you find it very difficult to do. There are designs to get 3 motors working, right, at a single point, and they are intersecting. The axes are intersecting. It's not easy, but in human body we have that kind of joints. But otherwise, if you look at general industrial manipulators, the designers and manufacturers, they don't want to go through this hassle. What they do is you have individual joints and individual degrees of freedom for each joint. Okay. So that's why I said number of joints is equal to number of links and number of degrees of freedom. So then the task definition. Usually in any industrial application, we define the task in workspace using XYZ coordinates and the orientations, right? You can assign velocities, positions, or accelerations when you plan the motion from one point to another. Just like in welding, for example, you need to move the end effector welding torch along the line from A to B at a certain speed. Okay. So these are kinematically modeled using equations, right? So when you really deploy a robot manipulator for application, right, you basically do 3 things. One is trajectory planning. You plan the trajectory from start to the end. Okay. So as I said, generally you define the task in XYZ hour space, but you already know that robots do not understand XYZ, but they understand joint angles. So you have to convert your operation in our workspace into joint angles using, if it is a 5 degree of freedom manipulator, 5 joints. So every step of the way, every 50 milliseconds or so, you have to update the joint angles, all of them. Okay. So then you have to program it into the programming platform of the manipulator, right? So there also you saw a video I showed you 2 weeks back probably, how you program a robot manipulator. What is the first point, second point, third, and so on. Then the robot understand these via points, and then it interpolate between points, uh, so many points in between, right? Maybe 50 millisecond interval, and it uses a velocity, certain velocity, and convert that into uh, based on the velocity, it calculates the position, probably taking 50 millisecond as the sampling interval. All right. So all these things are pretty straightforward things. You need to stack them on top of each other. So once you have the trajectory defined at a higher level, you can break it down into via points and samples of 50 millisecond interval. Okay. Then comes motion control. So once you plan your trajectory, you are asking the robot controller to drive all of these joints, maybe 5 joints, to a certain angle initially. Maybe you can start with 0, 0, 0. So all zeros, right? So it may be vertically upward position of the robot or vertically downward position of the robot, right? So that is your start point. And then from there onwards, the data file has the 50 millisecond position updates, coming from what you have already programmed. Okay. So these things are actually embedded into the motion control system of the manipulator. You don't have to manually do that. All what you need to do is to specify as the wire points, right? And after that, the control part of the system will make sure that the robot moves from one sampling point to another next sampling point within, say, 50 milliseconds. Okay. So it has PID controls, independent joint motions, right? To make sure each joint follows the trajectory. So that's how it happens. So here is the two spaces. On the left, we have joint space, joint angles, and on the right, you have task or Cartesian space. All right. So once you define your task in the Cartesian space, you need to transform it to the joint angles, and we call it inverse kinematics. Inverse kinematics. And if you have the joint angles, to calculate the end effector position, right, in X, Y, Z, is called the direct kinematics. Direct kinematics, okay? So we can simply generally describe the forward kinematics using this equation, R equals function of Q. So what is that? Q is the joint angles, right? This one is joint angles. All of the joint angles from Q1 to maybe Q6. If it's a 6 degree of freedom manipulator, 6 joints, what are their angles, right? Once you know that, there's a set of equations here. F is a functional, right? Functional means not just a function, it's a collection of functions. You can write it down like F1, F2, F3, F4, like that. And R is your joint space, sorry, your Cartesian space. Okay. So how do you define your Cartesian space? Maybe it's the X coordinate, Y coordinate, Z coordinate, and orientation. Using whatever format you want to define the orientation in. Maybe you can get the roll picture, three angles, or anything else for that matter, right? So all that connected together, assembled together is R. That is the description of the um, position and orientation in Cartesian space. All right. So this is somewhat easy. This problem is easy, forward kinematics, whereas inverse kinematics is not easy. It's difficult to solve. I think earlier we looked at that problem, right? So most of the industrial manipulators, right, what they do is a very simple technique is that um, once you bring the manipulator to wire points, point 1, point 2, point 3, and so on, robot manipulator, right, it doesn't know X, Y, Z. Where you brought the end effector to. Robot doesn't know. But robot can read the joint angles. The first joint angle 30 degrees, second joint angle 50 degrees, like that. It can measure all of these joint angles. That's all what it needs. At any later time, if you want the robot to go to point 1, all what the controller does is it records the joint angles, right? And then drives the angles to this what you have previously recorded. So then naturally the end effector will be positioned in that point 1. Second, third, fourth, all of the points it remembers like that, controller. And after that, it plans from one joint configuration to the next joint configuration, all in joint space. So here you can see one joint angle vector, Q, Q1 up to Qn. So these are the joint angles, okay? First joint, second joint, third joint, up to nth joint, all of these angles. So once you know the angles, if you know the angles, like for example, in teaching, you bring the end effector to a certain point and push a button saying that this is my first point. Immediately, the controller reads the joint encoders and find out these angles. So you know this Q. Controller knows this Q and it can calculate if it wants R. What is the end effector position and orientation? using this functional, right? And today we are going to look at this function. How do we create this function f? It is the single most important question for this lecture. Forward or direct kinematics. Okay. So the reverse problem, you specify R. You say, okay, I want the end effector to be located at this point with this orientation, right? So you define it using these variables, R1 to Rn, right? And then using this as the input to the argument, this time it is inverse functional, F inverse, you can calculate Q. If you want to do it mathematically, you need to have this model, right? And getting inverse is difficult, that one. Therefore, what happens in real robots, it reads the joint angles, right? And record it like that. So this recording joint angles and putting it there is good for industry, for most of the industrial applications. This accuracy is okay, but you are really serious about the accuracy, right? You should not do it that way, right? You need to have a very accurate model of the manipulator. And then once you have this F, right, you can put your R in and calculate Q mathematically, not just by reading the encoder. Okay, so this is there you can see how a serious research is done and how not very serious industrial application is developed. So this is the difference between the two. Then the parameter Q is the joint angle vector. You can, sometimes you might wonder why not theta, because we have been using theta for angles for so many years, right? So when you say, when you hear the word angle, what comes to your mind is theta. But here it is Q. It's different. The reason is some of the joint angles, some of the joints are actually not rotary. It can be prismatic as well. So then we need a common variable for joint variables, right? We call it joint variable. It can be angle or distance. Right? That single variable needs to take two different positions, angle and distance, depending on the nature of the joint. So if we keep using theta as joint angle, we are actually treating playing for only the rotary joints, all rotary manipulators, because obviously you cannot use theta for a prismatic joint, and prismatic joint is a distance, right? So that is why we use Q. Remember that, okay? Q is theta for rotary joints and Q is D, distance, for prismatic joints. Okay, so R, as I already explained, it is how you define your Cartesian uh, position and posture, okay? So we call it position and orientation. So the pose, right? So the way you describe it. You can describe the manipulator in whatever form you need. And I think you know this one. M should be less than N, right? Or minimally it should be 6. If you really want to uh, control the pose arbitrarily, which means any position with any orientation, without any restriction, you need to have at least 6 joints. Okay, because in three-dimensional space, you have 3 coordinates, x, y, z, and 3 angles, roll, pitch, yaw, right? So 6 variables are required. If you want to calculate 6 variables independently, you need to have 6 variables in your joint space as well. Okay. So Here the n, letter n, is the joint, number of joints in the manipulator. It should be greater than or equal to simple m. Simple m is your dimension in your application. Now you might wonder why m? Because m is 6. For a lot of applications, you understand this as m equals 6 because 3 position variables and 3 orientation variables, altogether 6. But it's not so. It depends on your application. Let's say you want to draw something on the wall using a robot manipulator. Okay. Um, if you have, let's say it's on the table, not the wall table. So you only need XY, right? You only need XY, and even Z you don't need. You can put the pen in that whatever position touching the paper, and after that you don't need to control the height. Okay, it's only at the start and end point if you want, right? After drawing, you want to lift the pen, that's all right. But for the operation, it's a constant Z. So what you're doing is you are changing X and Y. Are you changing the orientation of the pen? No, you don't have to. So therefore, it is just a 2 degree of freedom application, right? Only two variables are there. So therefore, in that case, m equals 2, not 6. But if you look at automobile industry, where you use a manipulator to do the spot welding. Remember, I showed you this video sometime back. In that case, you need to be able to control or position the manipulator end effector arbitrarily in three-dimensional space, X, Y, Z, with arbitrary orientation. So you need 6 degrees of freedom. So it depends on the application. Right. Now, with all this information, let's look at this diagram. Right? This is the robot manipulator, right? And this is the base, right? And you have this link, base link, and this is the first joint. We call it Q1, right? So it has this angle, and then at the end of that link, right, you have the second joint, and then joint angle is Q2. And here the third joint is different to this one, and this one is a sliding joint or prismatic joint. So the joint variable is a distance. But using this generalized coordinate Q, you can name it Q3. So it's a linear motion. And then the fourth joint at the end of that link, right, is a rotary joint again. We call it Q4. And it goes on like that. And at the end, you have the last joint, nth joint, right? We call it with the name Qn. So this is the manipulator from here to this point, right? Now, if you look at this one, right? We start the joint with number 1, first joint. There is no zeroth joint, right? You have the first joint. And after that, you have the first link. This is the first link. So joint and link, like that. Then what about this one? Without a joint. This is the base. You can say zeroth link if you wish, okay? It's the base. You have to remember this convention. Because some time back, when I was teaching the Craig's convention, it was not like this. It's different, okay? This is the standard DH representation. You have the zeroth link, that is the base, which is not moving. And then you have the first joint, first link, second joint, second link, and so on. And nth joint, nth link. Now, this is just a link where I have this mouse pointer. This is just a link. You can't do any work using this kind of manipulator. with just a link at the end. So what you do is you attach a end effector to this one. The red frame here is the new end effector that you attach to the manipulator. It can be a laser cutter, right? Can be a gripper like this, what you see on screen, can be anything. So you already know that if you want to describe the pose of an object in three-dimensional space, you need to attach a coordinate frame to that you know, right? The origin of the coordinate frame is the position of that object in space. And when you have x, y, z axis oriented in three-dimensional space, that is the orientation of that link, right? An object can be placed in any x, y, z point, but with different orientations, vertically up, vertically down, horizontal, right? Like that. So the orientation is the orientation of this coordinate frame attached to the end effector. So there is a coordinate frame here. There's a coordinate frame here. At every joint, there's a coordinate frame. Okay, this is the last joint, there's a coordinate frame, and after that, you have the end effector, and there's a coordinate frame attached to that as well. So below here, you can see different applications, right? Where you want to draw something on paper, on horizontal plane, right? Your task space, your workspace is two-dimensional. And if you want to control the orientation also in a certain manner, you need to add another dimension, right? It will be three-dimensional. So then there's orientation also. Now, if you think of application like spot welding, for example, positioning and orientation in space, you can increase the dimension to 5. And this is completely arbitrary positioning and orientation, right? Positioning of 2 points in space, end effector and elbow, right? M equals 6. This is completely arbitrary orientation control, position control in space. You need 6 degrees of freedom, right? Okay, now you can see some of the typical designs for manipulators. You have seen these things earlier also, but this is more descriptive. You can see linear motion along this direction and linear motion lateral to that, and also up and down motion. This is PPP, prismatic, Cartesian or gantry type manipulators, right? And the second one over here is a cylindrical because it has a rotary joint at the base and then 2 linear motions. It is RPP. This one is Carrar manipulator. There you can see 3 vertical axis joints. First 2 are rotary. Third one is prismatic. It goes up and down. These 2 are rotary. So by changing the nature of the joints from prismatic to rotary, you get very different motions, right? This is spherical, in line with the polar coordinate system. 1 rotation, basically 2 rotations and 1 prismatic joint, right? And this one is the articulated or anthropomorphic manipulator, very much like human hand, right? So very complicated, but it's very efficient and compact compared to other manipulators. So let's start the discussion with the mathematical discussion of direct kinematics. Let's start with something simple that you all can understand very easily. So look at this manipulator, right? Sometimes we don't want to call it a manipulator, so simple. It's a two-link manipulator, right, in a vertical plane. This is the first link, L1, the second link, L2. Right? And at the end, you have the end effector attached to it. So this green coordinate frame here is the end effector frame. Okay. So there's a frame here for the link 1. There's a frame here for the link 2. Two-link manipulator has two frames, two coordinate frames, one each uh, for each link. Okay. But there is another one at the end, that is the end effector. Now, so what is my joint coordinate vector, which is Q? This is joint coordinate vector, right? I have two joint angles, Q1 and Q2. So Q1, I measure from the horizontal position. So this is my convention. I declare my world coordinate frame, this one. You can see this X and Y, this coordinate frame, right? As the base coordinate frame. So if I move back a little bit, here, this is the base. Sometimes you can call it link 0, that's fine, but this is the base basically. So base got to have a coordinate frame attached to it. Where do you attach it? Sometimes you say at this point, on the point on the ground where the base is attached, right? This is the origin, and then what is X? Maybe horizontal direction X, vertical direction Z, and into the board is Y, X, Y, Z. So you have to assign a coordinate frame to the base, to the ground. You can call it the earth frame, right? The reference frame. And then at the end of the base, you have the first link. And at that point, you have the first joint. There you define or declare another coordinate frame. And that is for the link 1. Link 1. So when the link 1 moves, the coordinate frame also moves, right? Because coordinate frames function is to describe the orientation, position and orientation of that link. Right. So here, the link 1, right, is like this. It has its own coordinate frame at this point. And apparently, we don't see a base here. Base link. What is the base here? I think there is a base, but the base has 0 length, something like that. Right? There should be a base now for every manipulator. It is this the point of attachment of the manipulator to the ground. So maybe somewhere here, this is the base. Right? It is 0 length, therefore we can't see it. But we can see the coordinate frame of that link, base coordinate frame. This is the X, this is Y. So the XY coordinate frame here is the base coordinate frame. Okay? All right. So this base coordinate frame is not moving, it is fixed. With respect to that, the link 1 rotates. Now at this moment, it has already rotated by angle Q1, right? So therefore, the coordinate frame of link 1, which is attached somewhere over here, has a different orientation with the base coordinate frame. Base coordinate frame is fixed, it's not moving. Whereas the coordinate frame attached to link 1 moves as the link moves. So therefore, even though the two coordinate frames coincide over here, share this point, common origin, but they are looking at different directions. So at this configuration, the joint angle vector is Q1 and Q2. It's a 2 degree of freedom manipulator, 2 joint angles. What about the Cartesian description? Which means how you describe the robot in Cartesian space. Well, for that, you can go to the endpoint over here and describe the endpoint. So measure the distance along x direction of the world coordinate frame, the reference frame. This is x, px, and vertical position is py, px and py. And also this orientation. The end effector is looking at a certain direction, right? From horizontal direction, angle of phi. So you can use these three rather, coordinates to describe the end effector. Px, py, and phi. Px, py, and phi. You decide how many, so what are the relevant parameters that you need to assemble together in this vector R, right, in order to describe the end effector in Cartesian space. Okay. Now, if you look at these two equations here, the number of degrees of freedom or number of actuated joints is 2. So it is n equals 2. And R, apparently Px, Py, Pz is 3, right? So therefore, this is some sort of violation, it seems, that earlier we said n has to be greater than or equal to m, whereas it seems violated here, but it's not actually violated. This m is actually 2, not 3, right? Because Px, Py, and Pz are not independent. You cannot have Px and Py and independent angle for phi or phi. Because the moment you fix Px, Py, you decide what is phi. It can have more than one solution, but it is defined. You cannot have arbitrary phi with arbitrary Px, Py. Or you can have arbitrary Px and phi, but then Py is already decided. You don't have any control over Py. So out of the 3 variables that you use to define the manipulator in Cartesian space, you only have good control over only 2 of them. Okay. Third one is automatically decided the moment you set the other 2 variables. I think you got the point, right? So therefore, m equals 3 is not very correct. So I'm sharing Alessandro's PowerPoint, so I'm not going to change it, but make a note that even though it apparently 3, it's actually 2. Now, if you write down the equations, forward kinematics, right, it's not difficult here, right? It's just trigonometry. Px equals L1 cos Q1 plus L2 cos Q1 plus Q2, right? That's the first equation. Now, Q1 is measured from the horizontal direction, but Q2 is measured with respect to the previous link L1, because as you know, the joint motor attached here, it rotates with respect to L1 because the reference for this motor here is L1. However, it has already rotated, doesn't matter. From that point onwards, uh, uh, this joint works, all right? So therefore, the reference direction for joint 2 is not horizontal. It is actually the previous link. So that is why, that is how joint 1 also got this Q1 because it's coming from its reference. The reference for joint 1 is actually frame 0. Frame 0 means this frame. This is the horizontal axis. Link 1 angle is measured from the horizontal axis to the link. And link 2 angle is measured from the link 1 angle to the link 2 angle. So therefore, it is like that. So that is why you get this Q1 and Q2 always. Okay. And what about vertical coordinate, Py? Again, it is sine format of the first equation, right? L1 sine Q1 plus L2 sine Q1 plus Q2. Now, once you specify Q1 and Q2, you specify Px and Py, and not only that, phi is Q1 plus Q2. This total angle, this is the orientation. So in this particular case, orientation is just one angle because it's a planar manipulator. On the plane, what is the angle? Okay, from the horizontal direction. Now, even though this is very simple, it is simple because the manipulator is so simple, just 2 degree of freedom planar manipulator. Okay. Most of the typical manipulators are not that easy. It's in 3-dimensional space. So it's complicated. You cannot actually continue or scale up this method to higher degrees of freedom manipulators. So we need something more elegant so that we can consistently apply for any manipulator. Okay. So, as I already mentioned earlier, there should be some sort of convention for all of us to agree and abide by. Without that, we cannot proceed this elegant mathematical framework. So this slide shows you that convention. You have the base. Let's call it link 0. Start moving. The frame attached to it is fixed. It's the reference, universal framework or earth framework. Okay. And then you have the first joint and the first link, second joint and the second link, like that. Okay. So if you look at the joint number, right, in blue color, these are the joint, red color are the links. So the link follows the joint. What comes first is joint and the link. In other words, the indices, if you take joint index and link index, right, out of these two, the joint index comes first. Joint and link, joint and link. Why I'm saying that is that in Craig's convention is the other way around. Okay. So please remember that, okay, because we are now going to double down on that, right? We are going to put a lot of things on top of that. And if your foundation is not very firm, you might find difficulties going forward. Then our discussion is joint axis. Joint axis. So if I give you a manipulator, you can identify the joints, right? It's pretty easy. Anybody can do that. And also you can identify the axis of motion, right? It's pretty simple. You can draw straight lines. Joint axes are straight lines. You can draw these straight lines. You can identify the first joint and joint axis, second joint, the joint axis, and so on until the last joint. There also you can draw the axis. Very easy. It can be rotary joint or it can be prismatic joint. Doesn't matter. Either way, you can draw the straight line, joint axis. So here you can see joint I. This is the axis. After that, you have the link I, because link follows the joint, right? Joint I, and this probably is a link. Okay. And this is the end of that link. There you have the other joint, next joint, the joint I plus 1. You can draw that as well. Axis, joint axis. So after that, you have link I plus 1. So it goes like that. Now, these two axes are the consecutive joint axes. One is along this direction, the other one is along that direction. What is in between? In between is the link. The in between is the link. Sometimes you might think, okay, these axes should be parallel to each other. Not so. right? Because there can be a twist in the link. The lower end of the link has a certain orientation. The upper end of the link over here, it can be twisted or rotated by 90 degrees or whatever, right? So if you want to relate these two axes by some means, we better use common perpendicular between the two axes. So if you get two straight lines in space, you can always find out the common perpendicular. The line which is normal to both of these axes, common perpendicular. And we give that length from this point to that point as the link length. Not the physical length from one end to the other end of the link, but the length of the common perpendicular. That's what we need for mathematical purposes. Okay, mathematical purposes. And also you can see in this particular diagram, the two axes are not parallel to each other. So therefore, there's a certain angle between them. And the name given is alpha I. This is link I, right? It has twisted from its lower end to upper end. There's a twist, and we give the name alpha for that twist. And it's an important parameter in each link. What is alpha I? First link alpha 1, second link alpha 2, and so on. Twist, okay? And then the distance from here to here is the length of the link, right? So it's a displacement from A to B. So the twist here, alpha, and the length of the link AB actually define the link. So you have n link manipulator, you have n number of links. Each link has alpha and A. Simple A means the length, and alpha is the twist. Okay. Two parameters, just two parameters to describe each and every link of the manipulator. The length and the twist. And when we talk about angles, remember, you know that the anti-clockwise direction is positive, clockwise direction is negative. Okay, stick to that one. Okay, now we are connecting links using these joints. Now what you see here is joint I, arbitrary joint I. So as you already know now, the link follows the joint. So therefore, after the joint, you have link I, the joint I and link I. So therefore, the previous link is link I minus 1. Now say I is 1. This is the first joint. This is the first link. And before that, it's 0 link. Link 0 means base. Okay, right. Now for any other arbitrary joint, I, it has a link before that, and there's a link after that. So you are connecting two links at this point. You can see these two links here. This is the previous link, this is the following link. Okay. So there's an angle here. Then this is what is called the joint angle. Okay. Previous link is like this, the common perpendicular, right? And this is the next common perpendicular. And there is an angle between them, right? Around this axis. Again, counterclockwise is positive, Clockwise is negative. This angle is theta. Not only that, the previous link, this one, comes like this at this point. It hits the joint somewhere here. And the following link starts at another point, because these links are physical links. They have their widths and height and all that, right? They're solid bodies, right? So the two links, when you combine together, probably you have to put one on top of the other. So when you do that, the following link is at a higher position than the previous link. So along the axis of the joint, link I is offset by a certain distance. Offset by a certain distance. So this distance we call offset is another parameter of the joint. Okay. So theta, joint angle, and d, joint displacement. Okay. Joint displacement or offset. So these two parameters define the joint. So for joint I, we have di and theta I. So now we have four parameters. Earlier, A and alpha, that describe the link, right? This one describe the link. And theta and d, they describe the joint. So in a manipulator, you don't have anything. All what you have is joint and a link, joint and a link, joint and a link. So if you can model the joint using these two parameters, that is d and theta, and if you can model the link using these two parameters, A and F, you are defining entire manipulator from base to the end effect. Now let us put all these four parameters together in a one single joint. Right, so you are seeing now the most important slide of this lecture. You have link I minus 1 on the left and then link I after that. In this particular case, right, link I is actually lower than link I minus 1. But mathematically speaking, that's not an issue here. And as you already know, the link follows the joint. So therefore, the lower end of the link is the joint. So link I minus 1 is this one. The joint I minus 1 is at the lower end of the manipulator. We assume the left-hand side is towards the base, right? This side is towards the base. So that's why this is I minus 1. This is I plus 1, okay? The left-hand side is base side. Right-hand side is the end effector side, okay? All right. Now, if we look at, as I always say, the link follows the joint. So we have to first declare the joint and then the link, right? Joint and the link. How do we define this joint? Well, it is using the joint angle and joint offset displacement. Now, here you can see this link I minus 1, right, is coming like that. This is the common perpendicular that represent link I minus 1. And this red one over here is this line represent link I. So two straight lines, this one and this one, right? And they are offset by a distance di. So this might confuse you because if you look at the diagram over here, link I is at a lower position than link I minus 1, right? But in the kinematic structure, link I is at a higher level than I minus 1. So this is probably a little mistake. It should have been the other way around. So this line would have been better had it been put like that, slightly below. Then it is very much in consistence with what has been drawn over here. Okay, but doesn't matter as long as you can understand that one. So there's a little offset di at joint I, and also these two links, right? They are not looking at the same direction. There is a little angle here. So if you extend the link, previous link, this one, right, and then put the next link, that is link I, right, at the same point of intersection here, joint axis, you can see how much the link has rotated, or link I has rotated with respect to link I minus 1. Okay. So again, clockwise is positive. Sorry, anti-clockwise is positive. Clockwise is negative. So if you look at this diagram, this is axis of rotation, right? And this angle theta I is negative actually. You can see that, okay? Because this is not the clockwise angle. Clockwise angle is the other way around. So therefore, this angle should be a negative angle. Right. So you also can see this O point. This is the origin. We call it origin of some point, some coordinate frame, intermediate coordinate frame, let's say, right? And then you move it upward over here, right? And then along this link I towards this point, and we call it OI. Can you see that? OI minus 1, OI. It's like that. Now, let us put the axis now, joint axis, say axis I, right? Along that direction is at I minus 1. This is very interesting, right? These are things people get confused very often. This is at I minus 1. At the end of the link, you have the coordinate frame. So joint follows, the link comes after the joint. And if you look at the axis, right, I, it has is at I minus 1. So sometimes you don't like this, right? It's a bit confusing. But this pays off. This has some advantage going forward, right? If you initially get adjusted to this convention. And also link I minus 1, this one, if you extend that line, right, it is xi minus 1, right? So the coordinate frame needs to have x, y, and z. But if you know two of them, you don't need to know the other one. It's automatically aligned. So therefore, we only consider z and x here, right? So at the end of the link, I minus 1, you have joint I, but do not get it confused with zi. In fact, it is zi minus 1. Okay. So there's no any easy way out rather than remembering it that way. Okay. And extended common perpendicular is xi minus 1. So that's all what you need to know. So I have the previous link and the coordinate frame attached to that link over here, and then move it upward. There is no coordinate frame at this point, and then move it along the link to the joint I plus 1. And at that point, you have OI, the coordinate frame of the link. So to put everything in line, I would say this. You have the joint axis and then the link. And at the end of the link, you have the coordinate frame. Okay. Again, you have the joint and then the link. At the end of the link, you have the coordinate frame for any I. So for example, if it is I minus 1, let's say this is I minus 1 joint, this is I minus 1 link, this is I minus 1 coordinate frame. That way you can remember it. Now this coordinate frame is important, OI minus 1 at the end of the link. And then it moves up a little bit and it rotates also, right? At this point, there's a rotation. In fact, we said I minus 1 is the axis of rotation, right? But what rotates is not this red line, but this red line, AI. So AI rotates around this red line, that is AI minus 1. And the angle is theta I. So there's a rotation here and there's a translation also, or displacement, right? And it gets to this point over here. And there's no coordinate frame here. If you want, you can put a coordinate frame, that's fine. But even without the coordinate frame, you can proceed. And after that, what happens is that the rotated coordinate frame moves along this line and gets to this position. And there you can see the twist coming up. So far, we have considered the angle and the displacement. Okay, that is the two parameters of a joint. Now, this is the description of a joint. What the joint does, it turns link I with respect to link I minus 1, right? And also it displaces link I with respect to I minus 1. So this is basically the motion. This is basically the motion of joint I. Okay, it rotates link I with respect to link I minus 1 by this angle. And also it moves up or down link I with respect to link I minus 1. Okay, these two. For rotary joints, theta is the variable. For rotary joints, theta is the variable, d is a constant. D is a constant. But for prismatic joints, d is the variable. This one is the variable and theta is a constant. So this is the beauty of this convention. You don't have to have different conventions for rotary and prismatic joints. The same convention, you can treat both rotary and prismatic joints. So the joint description is over. After the joint, what comes is the link. Link has two parameters. You know that, right? How long the link is. This length is important in describing the geometry. So we need to take this link length AI. Not only that, if there's any twist between the start point and end point of the link, link I is our link of interest. If there's any twist of the other end of the link with respect to the lower end, right, you need to put that into the geometry. So the length and the twist are going to come into the discussion now. Right. So the displacement, how far you want to bring this coordinate frame along this line, right, matters. And then at the end point, you can see the joint I and here joint axis I plus 1. They are not looking at the same direction. They are not parallel. There's some sort of twist. And that is that angle alpha I. Okay, that is at angle alpha I. So you need to put that also into your mathematical model. If you can do these 4 operations mathematically, right, all what you need to do is to repeat that from base to the end effector. Joint, link, joint, link, joint, link. Get these pairs from the base to the end effector. You are done. You're done. So now I'm going to ask you to write this little exercise. During the break, you can do that. We can take the break and the exercise together. Can you define mathematically these 4 parameters, theta, t, a, and alpha? Theta, d, a, and alpha. To help you, I'll tell you the answer for the first one. Say theta. What is theta? Theta is the angle. Theta is the angle, right? From xi minus 1 to xi, isn't it? This is x minus 1. This is xi minus 1 to xi. So theta I is angle from x minus 1 to xi around zi minus 1. So that is the mathematical description for theta I. Okay, telling again, theta I is the angle from xi minus 1 to xi around zi minus 1. Similarly, can you write down the mathematical description for d, a, and alpha? Right. Give it a try. We're going to take a break now, about 10 minutes. And after 10 minutes, with your answers, we'll meet up again. By the way, any questions? Now you have the definitions for all 4 parameters, right? For example, theta I is the angle from xi minus 1 to xi around zi minus 1, because the angle is happening at this point, joint I, right? At this point, coordinate frame is at I minus 1, I minus 1. And then the distance di is the distance from xi minus 1 to xi along zi minus 1. Now, if you look at these 2 motions, they are all with respect, they are both with respect to zi minus 1, same axis. With respect to the same axis, zi minus 1, there's a rotation, there's a displacement. Okay. And then what happens? AI is a distance, is the distance from zi minus 1 to zi to this point. From this point to this point, this is the distance of the common perpendicular, in fact, right? Along xi, along xi. And then at the end, there is a rotation from zi minus 1 to zi around xi. Now, if you take the first rotation and translation, they're both with respect to zi minus 1, and the latter translation and rotation, right, this one, are with respect to xi, right? The latter 2 motions are with respect to xi. In fact, I don't want to call them motions because there's no motion there. It is the length of the link and the twist of the link. Okay, but if you imagine this as a motion, right, you can see the motion along xi, rotation along xi. So similar to previous rotation and translation with respect to zi minus 1. The first two rotation and translation, right, are physical motions, right? Actually, one of them is physical motion, the other one is fixed. As I said, if joint I is rotary joint, then theta I is the variable and di is fixed. Okay, only one of these parameters is varying. Okay, the other one is fixed. And the other later two parameters, AI and alpha I, they are both fixed by design, the length of the link and the twist of the link. Okay, right, fine. So in mathematics, if you have a rotation and translation with respect to the same axis, we call it screw operation. Screw operation. So here you can see one screw operation because there's a rotation and translation with respect to z-axis here. And at this point, also you can see the displacement and the rotation with respect to xi, the same axis. So it is also a screw operation. So these two screw operations bring this coordinate frame over here. You can see it over here, right? This coordinate frame, I minus 1, coordinate frame I minus 1 to coordinate frame I. So frame I minus 1 is actually the link I minus 1. Okay, end of the link. And frame I is actually the link I, this one, right? End of the link. Now you can see, now we have mathematical description from one link to the other link. This is exactly what we were looking for. Some mathematical foundation to relate one link to the adjacent link. When I say one link, I'm referring to the coordinate frame of the link. In this particular convention, coordinate frame of the link is attached at the end of the link over here, right? So frame I minus 1 to frame I. This is all what you need to know. So now it boils down to one single question. What is the mathematical description for the first screw operation and for the second screw operation? Again, if you know how to write a screw operation, it is just a repetition of that here, right? First, you take the joint parameters. Later, you take the link parameters, right? The two screw operations. Is everything clear before we proceed? Any questions? Do you understand everything we discussed right now or up to now? No questions? Right. Let's move forward. This is the same illustration, slightly differently. So now we have the link I minus 1, link I, and this is the coordinate frame of link I minus 1. This is the coordinate frame of link I. Now see, from here to here. Okay, we have 4 parameters. 2 of them are joint parameters. The other 2 are link parameters. And the first 2 parameters form a screw operation. Second 2, so does the second 2 parameters. Now, if I do a little bit of a math description, these are the points. Unit vector Zi, which is this one, right? Zi is along axis of joint I plus 1. So this is joint I plus 1. And the axis is Zi. So there is one less. If you get the joint axis and one less is the coordinate frame. Okay. If you go to, say, fifth joint, if you go to fifth joint, the coordinate frame there is fourth coordinate frame. Okay, so it is the lower link here, the coordinate frame of the lower link. You have to remember that. Okay, the conventions are like that. You can't, there's no way to derive, you just have to remember it. That is how we assign frames. Unit vector xi, where is xi? This one, unit vector xi. Now, before you come to this joint is the link, right? So it is the extended common perpendicular is actually xi, right? You have the common perpendicular from here to here, and you further extend it in the same direction, and that is xi. In fact, this is the reference axis for any rotary motion over here after the successive link. Okay, so it's a common normal to joint I and joint I plus 1 axis. Okay, I plus 1, I is a common perpendicular, and it is in fact the distance is link length. So AI is the distance DOI. This is D to OI. See, from this point to this point. OI is the origin of the ith frame. Ith frame is the coordinate frame attached to link I at the end of the link I. D is not a coordinate frame. It's just a point. Okay. So this point is a variable. If this joint joint I is prismatic, if this joint is prismatic, then point D moves up and down as you actuate this joint. Axis of motion is this axis. If this joint is rotary, D is fixed, constant, but theta is a variable. Alpha I, where is alpha I? It's over here. It's the twist of the link I, right? Because the two endpoints are not parallel. There's a twist between them. So, and that twist angle is alpha I. Theta I is the angle from xi to xi minus 1 to xi, as we already wrote, right? Your definitions. All right, I think this is a good record for you. Now, let me show you this little video on coordinate frame assignment. Do you hear the sounds? I don't think so. So let me share the screen again with sounds. So watch this carefully. This explains you how you assign the axis for the joints and how you identify the DH parameters, the 4 DH parameters, okay?
Dedekind-Hardenberg parameters allow you to succinctly describe the motion of a series of rigid joints. This is useful for efficient calculation of forward and inverse kinematics. The process begins by defining the z-axis, along the axis of rotation for revolute joints, or the axis of translation for prismatic joints.
Now you can see over here, on the left is the base. On the left is the base. You have to assign a coordinate frame for the base also, and it is fixed. And then this is the link 1, okay, link 1. And in between you have the axis. This is the first joint axis,
Since this is the first joint, the x-axis is a free choice. For later joints, each x-axis will point away from the previous joint. The y-axis simply completes the right-handed reference frame. Now if we add another joint, we can determine the transformation between them. As before,
now you can see this is the second joint, and there also you can identify the rotation, axis of rotation. The blue ones, the moment you see the manipulator, you can draw these lines, okay?
The z-axis points along the axis of rotation. The dh parameters will be derived from the common normal between these z-axes.
Now you can see the common perpendicular, right? Common perpendicular. So your first joint axis, this z-axis, and the second joint axis, this z-axis. You draw them, and then this is the common perpendicular. And we take this as link length. Link length. Mathematically speaking, this is the link length. Does not have to be the physical length of the link from here to here. That you need to remember, okay?
The common normal is orthogonal to both vectors, and is also the shortest line between them. The new x-axis points along the common normal, and has its origin at the intersection with the new z-axis. Notice the origin is not within the physical actuator, because the dh parameters are only concerned with the motion of the links, not the physical placement.
There you can see the axis, extended axis. This is a common perpendicular, and you extend it from there, and that is the x-axis.
Components. Using this protocol for laying out the reference frames, only 4 parameters are needed.
Now you can see the previous x-axis, this one, right? This is the previous x-axis or the base coordinate frame. It is fixed, it's not moving. Okay, but this one is moving. This x-axis is moving, right? So between them, there is an angle.
The first of these, d, is the depth along the previous joint's z-axis, from the origin to the common normal.
There you are. Can you see that the displacement, right? What happens in one joint, right? It combines the previous link to the new link along the axis of motion, and the displacement is d.
Theta rotates about the previous z-axis to align the x-axis.
Can you see that the previous x-axis, the new x-axis, right? The angle is theta.
R is the length of the common normal itself. Most texts call this parameter a, which is unfortunately easy to confuse with alpha. Instead, calling it r.
Now this is the length of the common perpendicular, link 1 length. In this video, it is labeled as R, but in our case, we call it A, okay?
R is a useful mnemonic, as this is also the radius of revolution for the new origin about the previous z. Finally, alpha rotates about the new x-axis to bring z into alignment with the axis of joint motion.
Can you see that? The previous z-axis is rotated around the extended x-axis to align with the new z-axis, okay? And that angle is the joint twist. Oh, sorry, the link twist. The link has twisted by this angle, so that the joint at the lower end and the joint at the upper end are not parallel. In this particular case, it is 90 degrees.
Now there's one special case, when the z-axes are parallel. Because parallel lines have an infinite number of common normals, you can choose any d value you like in order to place the new origin at a convenient location, such as the center of a link or the tip of an end effector. The other parameters are the same as before. Theta rotates about z to align the x-axis with the normal, and r translates out along the normal to reach the new origin. Alpha is already known to be 0 in this case, since the z-axes must be parallel for this to apply.
So if two consecutive z-axes are parallel, which means you don't have to rotate the previous one to fall align with the new one. So angle is 0, alpha is 0 in that case. All of the parallel axes, alpha is 0.
No rotation is needed. Congratulations, that's all there is to it.
All right. Now you are familiar with the geometry. Now it's time to describe these operations mathematically. Right. So now I'm trying to write down the transformation matrix that we have learned in previous weeks, right? Try to relate joint coordinate frame I minus 1 to I, right? I minus 1 to I. So I take I minus 1 as the reference for the previous and I as the new. But now I understand that this is a two-step process. First, I I want to bring this coordinate frame from here to the point of D, right? The point D. And after that, I have another screw operation to bring it to I. So it is I minus 1 to I in two steps. I need to figure out the first step. I need to figure out the second step as well. So here you can see the first step. After the first screw operation, the coordinate frame is labeled as I dash. I dash is the intermediate coordinate frame when the origin is located at point D on the same Z axis. Okay, Zi minus 1. Now on the right hand side, you can see these two matrices. Can somebody guess what these two matrices are? What is the first matrix? Can somebody tell me? What is this first 4 by 4 matrix? No idea? You have seen this before. Just a couple of weeks back. So let me open MATLAB. While MATLAB opens up, let me show this again, right? The first operation is this angle theta, right? The first operation is a rotation around Z axis by angle theta. Rotation around Z axis by an angle theta. So in MATLAB, we can find that out. Some T is the command, robotics toolbox command for rotation around Z axis. Okay, homogeneous transformation matrix of a rotation around Z axis. Let me give an angle, say pi by 3. Okay, so this is what I get, right? Look at this configuration. Right? This is in fact the first matrix here. You can see cos theta, sine theta, minus sine theta, cos theta, and this structure again. Okay, can you see that? Cos theta, sine theta, minus cos theta, sine theta, and this is the structure. So what is it? It's a rotation. It's the rotation around Z axis by some angle. Okay, so what about the second matrix here? Can anybody guess that one? What is that?
Translation along is
Exactly. This is the translation along Z axis because you can see over here the 3 by 3 matrix on the upper left corner, 3 by 3, is a unit matrix or identity matrix. Therefore, there's no rotation. But the last column, you can see 0, 0, di. So first 0 is x-axis, second 0 is y-axis, third one is the z-axis. This is a linear motion along the z-axis by a distance di. Okay, so if I go back, it is this distance, translation along z-axis. So it brings this coordinate frame with OI minus 1 to this point with the rotation. So it performs the rotation and translation. So in MATLAB, you can figure that out, right? The command for that is trans a translation, let's say 0, 0, 3, whatever, right? So that is the translation operation. Now, if you combine these two together, right? First one is rotation, and second one is translation, 0, 0, 3, whatever, right? This is the screw operation. There you can see top left 3 by 3 part is the rotation part, and the fourth column, first three elements, is the translation, 0, 0, 3. Okay. So this is the first screw operation, rotation and translation. Now, if you get the order reversed, if you put the rotation part later and translation first, still you get the same answer because the screw operation is commutative. You know, in linear algebra, commutative operations means you can swap the two together, first and the second one, still you get the same answer. Okay, not every matrix operation is commutative, but screw operation is commutative. Then the second one is round and along xi, right? The second screw operation is with respect to x, not z. You remember that, I think, right? It's a translation along x-axis, xi, and then rotation around x-axis. So in MATLAB, you can try it out. So let's say translation, right, along x-axis. So let me give some number, 2, 0, 0. Is a translation along x-axis multiplied by t rot x this time, right, by a certain angle. So let me give pi by 4. Okay, and that is the second screw operation. You can see the top left 3 by 3 matrix. It has a lower 2 by 2 portion with some numbers, and you can see x-axis last column 200 is the translation. Okay, so pretty much in line with this one. Can you see that? This is the translation along x-axis. This is the rotation around x-axis. The lower right 2 by 2 partition of the matrix has some numbers. Other ones are 100 and here 00. Okay. Now, if you put them together, you get the complete description um, from I minus 1 to I, right? This one, I minus 1 to I, right? By multiplying the two screw operations together, and you get this one. So in MATLAB also you can see that, right? So earlier you had this one and then multiplied by what? Say a translation 200, and then another one t dot x, okay, pi by 4. So if you want, you can make it like this, so that you get absolutely sure that these two operations are done separately and then multiplied together. Okay, otherwise you get the same answer. Now, I want you to do a homework, that is, do this with symbolic mathematics, right? In MATLAB, you can use sims, say theta or something, symbolic command, right? Immediately you can see th coming over here, and after that you can put it to t dot z, rotation around z axis by angle theta, right? And see that this is symbolic. Earlier I used some numbers for angles, now it is symbols, right? So if I do this using symbols, right, I need two symbols, theta. So theta, and the other one is alpha, al, right? So I define two symbols now. You can see on the workspace, al for alpha, th for theta, and also another two symbols for the displacement. What are they? D and A. Okay. Right now I have all four DH parameters, A, alpha, D, theta. Now I can go ahead and create the entire transformation. How? T dot Z, right? Theta times translation by distance d along z axis, so 0, 0, d, right, multiplied by, to be on the safe side, it has put another bracket so that these two are operated separately, right? So there we have translation. Again, you can do the rotation first. This time it is along x-axis, so it is a 0, 0, right, times then the rotation, last one, so it is t rot x by alpha, al. Okay, now this is the answer. This is the homogeneous transformation matrix between frame I minus 1 and frame I. Right, over here you can see the same thing. So the homework I want you to do is do it mathematically. Multiply and check your answers, right? How? First, you write this one, T dot is it, theta, right? Oops. T dot is it, right? Basic rotation matrix, this one, right? And then multiply it with uh, translation, this one. Okay, so you multiply these two matrices and then do the same for the lattice screw operation and then multiply them together. Okay, analytically using symbols, right? A, B, theta, etc. And find it out for yourself whether you get this answer. Okay, so I will put that as an assignment on the Moodle, so that you can upload your answers, right? Is there any questions about the assignment? It's basically analytical derivation of the homogeneous transformation matrix of the DH representation of serial link manipulators, mathematical description between frame I minus 1 and frame I. Any questions so far? Is everything clear? Sandrovan, is everything clear or anything that you don't understand? Sandrovan, can you hear me? Panuka, is that clear to you?
Yes. Yes, correct.
Okay. Darshana,
Yes.
that's clear. Chamir, is that clear to you?
Yes, sir.
Okay, all right. Now, uh, now if you start from the base, there you can see the base coordinate frame, x0, y0, z0, right? And you know that out of the four parameters, right, theta, d, a, alpha, only one is a variable, other three variable parameters are fixed. Then you can write down the next coordinate frame with respect to 0. Okay. And then you can combine the first frame and the second frame. And you can write down second frame and third frame. Between any two adjacent coordinate frames, you can write down this homogeneous transformation matrix. So when you have 6 degrees of freedom manipulator, 6 links, 6 coordinate frames, you can write 6 of these. The first one, 0A1. Second one, 1A2. Third one, 2A3. Fourth one, 3A4. Fifth one, 4A5. Sixth one, 5A6. Like that. 6 of them. And when you multiply them in a series, you get 0A6. 0 means base, 6 means the last coordinate frame towards the end, at the end of the link. At the end of the link. So this is exactly what you want to find out, right? Where is my end point? What is the heading of that end point? So here you can see that, right? This series multiplication over here, right? You can see here 0A1, 1A2. It goes like that up to n minus 1 an. This is the last coordinate frame, right? And also you can see something before that and something after that. These are optional. So optional things, right? If you have a world coordinate frame somewhere here, which is not the base coordinate frame, you better get this transformation up here, right? Let's say you have multiple robots working, and each of these robots has its own base with respect to which all the other coordinate frames are described. But because you are dealing with multiple manipulators, you need to have a common reference coordinate frame like this over here. So therefore, for each robot manipulator, there is an initial coordinate transformation, right? Which brings the zero frame of the manipulator with respect to the world coordinate frame. Here it is RFW, right? Let's say W, for example. So that is why you have this coordinate frame over here. You have to physically measure the distances and orientation differences if there's any, and you have to manually fix that for each manipulator in your workspace, and it's a fixed transformation. And every manipulator, when you purchase, it doesn't come with the end effector generally, but certain manipulators specifically designed for a particular application actually come with the end effector. For example, a welding robotic arm, it usually comes with the grip, the welding torch, right? So either from the same manufacturer, or you can purchase it from a separate manufacturer. They are compatible. It's very easy to interface that. Now this end effector is attached to the end of the manipulator, right? End of the manipulator, that is over here. So this is the end of the manipulator, right? And at that point you attach this gripper or something, right? And the transformation from the last coordinate frame to the tool center point, this point, tool center point, is defined by this transformation, NTE. Again, that is also something you have to manually find out using by measuring the distances and so on, right? And it's a fixed thing afterwards. So with that, with those two transformations, you are good to go. You have WTE, which means the transformation from the end effector to the world coordinate frame. The moment you execute this one and get the numbers, you know where the end point this one is, right? And where it is heading with respect to the world coordinate frame here, not the base, but the world coordinate frame. Okay, so there, the first transformation and the last transformation are manually determined, and in between you have n number of transformations, homogeneous transformations. They are coming from the joint configuration. What is the first joint variable? What is the second joint variable? Third, and so on. And what are the link lengths, joint offsets, etc. Twist, okay? The parameters of the manipulator. Now, once you calculate the right-hand side of the equation, this one, you end up with WTE. So that is end effector with respect to the world coordinate frame, and it is a 4x4 matrix. It's a 4x4 matrix of this configuration. There you can see the top left 3x3 matrix is the orientation. Remember the orientation that we discussed some time back, right? It has 3 columns, right? And then the last column here, 3x1 vector, is the position. So the moment you calculate this one, you know the position. All what you need to know is to look at the third column, the first 3 elements, x, y, z. So that is the end point, this point with respect to the world coordinate frame. Okay, you know the position. But if you want to look at the orientation, right, you have to look at the top left 3x3 matrix. It has 3 columns, first column, second column, and third column. What is the first column? First column is the normal vector, second column is the sliding vector, third column is the approach vector. And they are illustrated over here. This is the end point, end effector. All right. So if you remember the configuration of the homogeneous transformation matrix, the top left 3x3 is the orientation, right? But what it really means is that you get the relative frame or moving frame, this one, it's unit vectors, right? It's unit vectors along x-axis, y-axis, and z-axis, and you write them with respect to the coordinate frames of the reference frame, right? This one. So here you can see the x-axis of the end effector, we call it normal, and y-axis, we call it sliding, and the z-axis, we call approach. Okay, normal, slide, and approach. These are the x, y, and z axis of the end effector. And we write with them with respect to the x, y, z of the reference frame, right? And you can see it over here, normal, sliding, and approach vectors. Okay. And this is 0, this is 1, this is P, the end effector position, this one. So this is basically the forward kinematics. Now, if you look at the same 2 degree of freedom manipulator or 2-link arm with a different perspective altogether, how do we use the Denavit-Hartenberg parameters or DH parameters, that is theta, D, A, and alpha for each joint and link, right? And then use the homogeneous transformation matrices to describe the forward kinematics. First, we sketch the manipulator and identify the reference frame, x0, y0, this one. And we don't have a world coordinate frame here, right? And we have the end effector here, which is actually endpoint of link 2. So therefore, we don't have additional end effector here. So therefore, the last transformation from the end of the last link to the end effector is also not there. So what we have is 2 links, 2 coordinate frames, 2 joints. So we prepare this table we call DH table with I, alpha I, AI, DI, and theta I, right? So these are coming from this illustration. Remember that, right? Theta, D, A, and alpha. If I go back a little bit, this way, theta, D, A, and alpha. You have to do this twice. First for the first joint, second for the second joint. Now you can see clearly, once you get this document, you can use the definitions of the 4 parameters, theta, D, A, and alpha, and find it out. But even without going that way, you can figure that out very easily. So this is joint 1, the first joint, joint 1. Okay, before that is link 0. You remember that. After that is link 1. And at the end of link 1, right, you have your coordinate frame. Link 1 coordinate frame is over here. Okay, and this is joint 2 or axis 2. Okay, but the coordinate frame is 1, first coordinate frame at the end of the link 1. And there you have the second link. Okay, and the end of that, right, is the coordinate frame of the second link. That is why you have x2, y2 up there. There is no join there. Okay, just the coordinate frame. Okay, at the end of the link 2. So if you look at the first row here, joint 1, I is the joint index, right? Joint 1, which is over here, right? You can see x0 to x1. This is x1. Remember x1 axis? The angle is theta 1. You can see it over here. Theta 1, we give it a name Q1. Q1, okay? First joint angle. And this is a rotary joint. All the other parameters, 3 parameters are fixed. This is the only variable. What about D? Is there any offset from x0 to x1? X0 to x1. In fact, physically, there can be that kind of displacement, but here we don't consider that. They are actually intersecting each other. They are intersecting each other. So therefore, there's no distance between them along z-axis. Z-axis is directly out of the screen, right? This is a planar manipulator. Everything is on the plane. So out of the plane is 0. So therefore, D is 0. What about A? A is the link length, right? There you move from here to here, from this joint to this joint, right? Along the axis, and this is L1. You can see it over here, L1. And at the end, you have the other axis. This is first axis, right? This is the second axis, right? And you have Z1 here and Z0 here. Z0 to Z1, right? They're both axes are out of the screen, vertically or normal to the screen. So therefore, the alpha is 0 because the Z-axes are parallel in this case. Z-axes are parallel. Right, now the second one up here. What is the angle from x1 to x2 now? X1 to x2 is theta 2. We call it Q2, right? The value angle is Q2. And x1 to x2 along z direction, vertically upward, is also 0. So D distance is 0. And then the length, Z1 to Z2. This is Z1 over here, Z1 to Z2. The distance is L2. And at the end, Z1 to 2Z2 angle. Again 0 because these two axes are parallel. There's no twist. The moment you see this kind of thing, all the Z axes are out of the board. This coordinate frame, last frame, second one, Z2 is also parallel. Right? We have placed this coordinate frame so that it is in line with the second one here and the 0 one here. 0 frame, first frame and second frame, right? Following the DH convention. So immediately you can figure out, even before doing anything, that alphas are 0. All the links, they are not twisted. Okay, both of these links are not twisted. So alpha is 0. Okay, so once you prepare the DH table, remember, you are supposed to be able to look at a frame like this, robot arm like this. Given the information, you are supposed to fill this table, okay, DH table. Once you have the table, you can write down the coordinate transformation 1 to 0, right? 0 is the frame here, 1 is the frame here. Using this 1, we have already derived. And then 1 to 2, any two adjacent frames you can write down, 0 to 1, 1 to 2, and then you multiply together, you get 0 to 2, right? 0 to 2. With respect to this point, what is the position and orientation of this coordinate frame, right? Like that, to get the answer. So from the answer, you can figure out the last column here, right? This one is the x coordinate. This is the y coordinate. Of course, we know z coordinate is 0. So you can put those coordinates here, and that is the position, right? That is the position of the endpoint here. So you can see here px, py, and 0, right? The position coordinates of the endpoint over here. In order to get that one, you can alternatively do this now. You have the coordinate frame here, transformation here, and you multiply any vector attached to this coordinate frame with this one pre-multiply, you get the position of that a point. So this point is actually 0, 0, 0, right? Like that, 0, 0, 0 is the origin of the coordinate frame here, right? You use as a vector and pre-multiply with 0, a 2, and you get this one, right? And effector position with respect to the base coordinate frame. And orientation is, of course, Q1 and Q2, addition of these two angles. Now, this is another example similar to the previous one, but there is an end effector attached to it. Can you see the end effector over here? Right, this is the second coordinate frame. Earlier, that was our end effector, right? Now, we have introduced another one over here, right? This one. So there is an offset from the second link, end of the second link, to the end effector. Maybe you have attached a welding torch which is curved like this, right? For some reason. So this coordinate transformation is not coming from directly from DH. That's the point, right? It's not coming from DH table directly. You have to figure that out. What is it? Can somebody tell me what is the relationship between these two coordinate frames, like coordinate frame 2 and the coordinate frame E? E means the end effector, right? Just by looking at this one, can you figure out the transformation between these two coordinate frames? Can somebody tell me, please? Can anybody tell me that, please? Look at the two coordinate frames, frame 2 and frame E. This one and this one. You can see XY of frame 2 and YZ of frame E. Can you figure out some sort of rotation? No idea? Can't you see a rotation around x-axis of frame 2, this one, around this axis? If you rotate by 90 degrees, what will happen? 90 degrees counterclockwise. You get the Z axis over here, right? Aligning this Z axis to this one. Because Z2 is out of the board. Z2 is out of the board. So it looks like there's a rotation around x-axis by 90 degrees. But that is not all, right? So after that, what will happen? After that, what will happen? There's another rotation to align this coordinate frame with this coordinate frame. The first rotation I spell out, it is around x-axis anti-clockwise by 90 degrees. You get Z-axis over here, align, and now you rotate around Z-axis, right, by 90 degrees, this time clockwise. Can't you see that? So these are the things definitely you need in robotics, right? You should be able to look at two coordinate frames and figure out how the first frame has rotated in order to coincide with the second frame, right? Because you have three axes, just three options, right? You figure out whether it is x-axis, y-axis, z-axis, or by how much. So I can see that if you rotate frame 2 here around x-axis by 90 degrees, followed by another rotation around z-axis by minus 90 degrees, you get the same orientation, right, as you see here in the end effector. So if I go to MATLAB and figure that out, what is this? T-rot. First one is around x-axis, I think, right? By 90 degrees. So it is pi by 2, followed by z-axis, around z-axis by it's minus pi by 2, right? So this is the answer. This is the answer. Now, if you check this answer, with this one, can you see the same thing, right? It is 0, 0, 0, 1, 0, 0, 0, minus 1, -1, 0, 0. Can you see that one? This one over here. So this is the rotation between second frame and the end effector. The moment you attach the end effector, you have to figure out what is the rotation and all, right? And there is certainly a displacement. You can see that, right? Certainly a displacement because two origins are not coincident. So there's some sort of, after orientation, some sort of displacement is there. Some sort of displacement is there. Now, what is this displacement? Now, after the rotation, right? This is YE, this is ZE, right? Now you can say that this coordinate frame is not here, but here, right? At the same point where second frame is located, right? But orientation of this orientation. Now you are moving along Z-axis, along Y-axis, some certain distances, right? Not along X2 or Y2, right? But along YE and ZE, right? You are moving along YE and ZE. When you do that, when frame 2 sees your motion, it sees as if you are moving along X2 and Y2. That's how it sees on the other coordinate frame. But you are actually moving with respect to this coordinate frame, YE, ZE directions. Okay. So let us introduce this displacement now. So it looks like there's a displacement around y-axis by some distance, around z-axis by another distance. Okay, so let us put that into MATLAB. Right, so I have the rotation and followed by a translation. This is the translation. There's no rotation around x, translation along x direction, but there's a translation along y direction. Let me put 2 units, and there's a motion along z direction. Let me put 3. Okay. So then I get this one. This is the answer. Right? And if you compare with this one, yes, pretty much aligned, right? This is the tool center point x coordinate. This is the tool center point y coordinate, x and y. So I moved, my motion is along y and z directions. But in the homogeneous transformation matrix, it appears along x and y. Can you see that? X and y. Reason is pretty obvious. When you are moving with respect to the end effector coordinate frame along y, it is actually with respect to along x direction in the second frame. When I am moving along z direction in the end effector frame, it is in fact negative y direction of y2. That is why you get this negative sign. Okay. See, -3. Now we have studied the DH parameters, DH table, homogeneous transformation matrices, and then also how to add an end effector, right? And how to figure out this coordinate frame from frame 2 to the end effector frame. Any questions, please? Samira, any questions? Sandrovan, any questions? Sandrovan? Banuka?
Okay, sir.
No question.
No questions? Chaturanga? Is everything clear to you? Chaturanga?
Yes, sir.
All right then. So let's wind up here for the day, and we'll continue next week. Thank you for joining.
Good evening, sir.
Thank you, sir.
Good evening.
Thank you, sir.
Thank you.